So now we'll state that what amount of heat is exchanged between the Carnot engines and the common reservoir R0. So till now we have said that what amount of heats are exchanged between the Carnot engine and their individual reservoirs R1, R2, R3 like this. Now we'll state that what amount of heat is exchanged between the Carnot engines and with the common reservoir R0. So let's say that the C1 Carnot engine exchange an amount of heat Q10 with the common reservoir R0. Okay, so again you see we are using the term exchange. Okay, we are not saying the whether this amount of heat is rejected or extracted or rejected to this common reservoir R0. So we are saying that there is an exchange of heat between the Carnot engine C1 and the common reservoir R0. So let it be Q10. And then the C2 Carnot engine exchange an amount of heat Q2, 0 with the common reservoir R0. So you see 1, 0 means 1 stands for the first Carnot engine, 0 stands for the heat exchanged from the R0 reservoir. Similarly, Q2, 0 is the heat exchange between the Carnot engine C2 and the common reservoir R0. So 2 stands for the second Carnot engine C2 and 0 stands for the R0, the common reservoir. Okay, so like this, so nth Carnot engine exchange an amount of heat Qn, 0 for the common reservoir from the common reservoir R0. Okay, so here we have another diagram which will show all these Carnot engines. Okay, as they are conventionally shown, the conventional diagram and with the exchange of heats. Okay, so here you see we have this C1 Carnot engine operating between the temperature T0 and T1. Okay, that is between the common reservoir R0 and the reservoir R1, and in doing so it exchanges an amount of heat Q1, 0. So this is Q1, 0 between Q1, 0 with the reservoir R0, and in exchange the C1 exchange an amount of heat Q1 with the reservoir R1. Similarly, the second Carnot engine C2 exchange an amount of heat Q2, 0 with the common reservoir R0 and exchange an amount of heat Q2 with the reservoir R2. Then C3 exchange an amount of heat Q3, 0 with the reservoir R0 and exchange an amount of heat Q3 from the reservoir R3. Okay, so like this, similarly same for the other reservoirs R4, R5, R6 and etc. Then the nth Carnot engine Cn exchange an amount of heat Qn, 0 from the reservoir R0 and exchange an amount of heat Qn with the reservoir Rn. Okay, so now the system K, so all this combination of the all n Carnot engines, this n reservoirs, individual reservoirs and this common reservoir. Okay, we know this makes up a composite system K. Okay, now this composite system K performs a complex cycle. Okay, and what is that cycle? In that cycle, each Carnot engine will operate the Carnot cycle only for once. And we know that Carnot engines operates on Carnot cycle. Okay, so in the complex cycle of the system K, each Carnot engine will operate for their individual Carnot cycle only for once. Okay, so in operating the Carnot cycle, suppose the C1 Carnot engine will exchange an amount of heat Q1, 0 with R0, perform some exchange an amount of heat Q1 with R1 and will perform some work. The amount of work done is not shown in this diagram. Okay, so similarly the Carnot engine C2 will also perform its Carnot cycle only for once. Okay, and then in doing so, in performing that cycle, it will do some work and exchange an amount of it Q20 with R0 and Q2 with R2. Similarly, the Carnot engine C3 will perform the Carnot cycle only for once, and in doing so it will exchange an amount of heat Q30 with R0 and Q3 with R3. Okay, so similarly all these Carnot engines will perform the Carnot cycle for once. Similarly, the nth Carnot engine will also perform the Carnot cycle only for once, and in doing so it will do some work. Okay, and it will exchange an amount of heat Qn0 with R0 and Qn with Rn. So it is said that now the system K performs a complex cycle consisting of n Carnot cycles by n Carnot engines each for once. Okay, so this complex cycle consists of n Carnot engines performing n Carnot cycles each for once. Okay, now the complex cycle is such that after completion of the cycle, the system K returns to the initial state. Okay, so there is no change, permanent change done in this system K, and no heat is lost or gained by the reservoirs R1, R2, R3, Rn. Okay, and so no heat after completion of this complex cycle, no heat is lost or gained by this reservoir. So we are not talking about R0, the common reservoir, but this individual reservoirs. Okay, so after completion of the complex cycle, no heat is lost or gained by this individual reservoirs R1, R2, R3, R4, R5, Rn. So you can say that after completion of the cycle, net exchange of heat for these reservoirs, individual reservoirs, is 0. Okay, so we are not talking about the common reservoir. Okay, so so what will be the operation of the each Carnot cycle for this each Carnot engine? So we know that so suppose if we have the Carnot engine operating between suppose temperature T1 and T2. Okay, and suppose it absorb an amount of heat Q1 from T2 does some work, suppose W1, and Q2 amount of heat is rejected to the reservoir at T2. So we know that Q1 by T1 equals to Q2 by T2. So here is a particular direction of flow we are showing. Okay, direction of heat flow. But in our diagram for the Carnot's theorem, we have not shown any direction of heat flow. But now the Carnot engine being reversible, it can perform the reverse process, right? So we have the same Carnot engine now performing the reverse cycle, like just in like a refrigerator. So it is acting between the temperatures T1 and T2. Now when it is doing the reverse process, so it will absorb an amount of heat Q2 from T2, some W amount of work, suppose let's only say W amount of work is done on it, and then it will reject an amount of heat Q1 to T1. So again, as it is the same Carnot cycle only in the reverse process, so this relation Q1 by T1 equals to Q2 by T2 is also applicable for the reverse process. So this is the forward process and this is the reverse process, but the relation is applicable for both the forward process and reverse process. Okay, and here this is the direction of the heat flow, and here this is the direction of the heat flow. So in general we can say that if Q1 amount of heat, so instead of heat absorbed in this case and heat rejected in this case, so here we are saying Q1 amount of heat is absorbed at temperature T1, here Q1 amount of heat is rejected at T1. So instead of saying heat absorbed or heat rejected, we can say that in general we can say heat exchanged at T1. Similarly, here we'll say that Q2 amount of heat is rejected at T2, and here we'll say that Q2 amount of heat is rejected absorbed at T2. So in general we can say, without being precise about this direction of the heat flow, we can say that Q2 amount of heat is exchanged at T2. So here what we can do, we can draw a generous diagram like we used for this system, where we have shown the amount of heat exchange between two reservoirs, but we have not shown the direction of the heat flow. So here we can say that we have this Carnot engine C operating between temperatures T1 and T2, and this Carnot engine will exchange an amount of heat Q1 at T1 and exchange an amount of heat Q2 at T2. Now the Carnot engine being reversible cycle, reversible, it can operate in forward process as well as in reverse process. So Q1 can be either heat absorbed or rejected. Similarly, Q2 can be either heat rejected or absorbed. But in general, it will obey this relation, which is Q1 by T1 equals to Q2 by T2, where Q1 is the heat exchanged at T1, Q2 is the heat exchanged at T2. So by this logic, we can say that, suppose if we look at this Carnot engine C1, so Q1, 0 heat is exchanged at T0 and Q1 heat is exchanged at T1. Okay, so for the Carnot engine C1, we can say that Q1, 0 by T0 equals to Q1 by T1. Okay, that is Q1, 0 will be Q1 by T1 into T0. So we are bringing T0 on the right hand side. Okay, so Q1, 0 equals to Q1 by T1 into T0. Similarly, for the Carnot engine C2, okay, so there can be either rejection or absorption of heat. Here can be either absorption or rejection of heat. We are not specifying that, but we are saying that Q2, 0 heat, amount of heat is exchanged by this Carnot engine C2 at temperature T0, at Q2 heat is exchanged by this Carnot engine C2 at temperature T2. So again, similarly, for Carnot engine C2, we can say that Q2, 0 by T0 is equals to Q2 by T2, which implies that Q2, 0 equals to Q2 by T2 into T0. Okay. Similarly, for the third Carnot engine C3, Carnot engine C3, third Carnot engine, Q3, 0 by T0 equals to Q3 by T3, which implies that Q3, 0 equals to Q3 by T3 into T0. Similarly, for the ith Carnot engine, we have Qi, 0 equals to Qi by Ty into T0. And finally, for the nth Carnot engine, we have Qn0 equals to Qn by Tn into T0.